So we just saw that the integral theta going from pi over 2 to 3 pi over 2, r going from 2 to 4 of 5 times x squared plus y uh, dA became 5 r cosine theta quantity squared plus r sine theta, all that in parentheses, and then the dA became r dr d theta. Now, I just would like to ask, oh yeah, and then here's a picture of the region of integration over on the right. But what I'd like to ask now is, how is the region of integration different? How is the region of integration different for a slightly modified integral? So I'd like to look at integral pi over 2 to 3 pi over 2, integral now 1 to 4 of otherwise all the same stuff here, 5 r cosine theta squared plus r sine theta r dr d theta. So how would the picture look? Well, instead of having, so it's really the space between two circles, yeah? But instead of going from 2 to 4, now what we should have should go from 1 to 4. So sorry if the picture doesn't look a whole lot different, but I hope with the labeling it will be relatively clear. Ooh, let's make that a little better though. Something like this. Maybe I'll shade this in a new color here. So the region still between two circles, just the left half, right? So it looks a lot like what we had before, just a little more space. We're going to lead up to an idea here. So let's play this game again and do the integral pi over 2 to 3 pi over 2, not from 1 to 4, but from 0.5 to 4. Otherwise, the rest is the same. 5 r cosine theta in parentheses squared plus r sine theta, close parentheses, r dr d theta. So what should be the picture here? Now, with a 0.5 radius circle and still a radius 4 circle, we should just have all the space in between. Okay, one last one. One last problem that looks like this. Let's draw the region of integration if we're integrating from pi over 2 to 3 pi over 2. Integral 0 to 4. Same integrand, same function to integrate though. Not that this part. Um, yeah, we're just drawing a picture of the region of integration. But let me copy this part all the same. R dr d theta. Okay. So now we're saying that the r value of the polar coordinate starts at 0. Well, that means the inner circle has radius 0 now. Well, it's just the point at the origin. We only have this part, circle of radius 4, and so we have this over here. So here's the point, is that what we had started with in a setup was looking at what if, r is a non-zero number like 1, just to hopefully see the picture better of what's going on. But if we keep closing up that radius a bit to get down to r equals 0, then we see that we end up having the entire thing. It's not like a little. It's like over here. These pictures look like a donut with a bit of hole to it, right? And then when you get down to r is equal to 0 as your starting point of starting r value of integration, then there's no more hole to this donut. It's a completely, it's like, yeah, there you go. So I guess I'll say you'd use r is equal to 0 when you know that there's no hole in the middle. That there's a way to take care of integration over a region where there's a hole in the middle that looks like a circle, and now there's a way to take care of integration if there's no hole in the middle. I'd like to find the volume of the space between z is equal to 1 minus quantity x squared plus y squared and z is equal to 0. So let's just draw a quick sketch of what this looks like. By the way, 1 minus um, x squared would kind of be a parabola. So x squared plus y squared, by the way, is, at least in the xy plane, the distance in the xy plane, the distance away from the origin, just in the xy plane. So what we really have is the height should be 1 minus how far away you are just in a horizontal sense from the origin. That's going to create a parabola-like shape. What we're actually going to have is, I'll try to draw this, is, well, you can plug in some points, yeah? So there's going to be a parabola along the x-axis, dotted because it's going to be behind, and then there's going to be a parabola shape in the y-axis direction. Let me extend the negative x-axis this way. And then if you rotate this around, it kind of creates a cap, yeah, or like an upside down bowl or something like this. So let's draw this in as well. Should be completely circular. So sorry if this picture's a little messy. Okay, so we want to find this volume. The region of integration. So we'll set up an integral, a double integral, and the region of integration. So we'll just draw this in the input space, x and y. It's actually going to be a filled-in circle. Yeah, this is going to be x squared plus y squared less than or equal to 1. Now, one way to set up an integral that's going to work. So let's just write the word volume here so it's clear what we're doing. There's so many pieces. Okay, volume. What we could do in principle is, based on this, say, hey, we need an integral that's going to end, let's say, dx dy. So then the y values would go between -1 at the smallest and +1 at the largest. -1 to 1. And then let's see, the upper x value and the lower x value. So I'm thinking about, this and that. So the lower part here would be negative root 1 minus y squared, positive root 1 minus y squared. And then we're trying to talk about the volume. So remember that the volume should, under a surface is the integral of this here as a function. So we should stick 1 minus x squared plus y squared here. Okay, so there it is. However, I'm going to say that trying to do this is awful. I mean, it'll work, I guess, but it's just going to be a lot of work. So instead, let's look at the region of integration and think about setting up a polar integral. Because if you describe this region here in polar integration, well, you need all values of theta, right? Because this goes all the way around, so 0 to 2 pi. And then values of r, well, there's no hole in the middle. This is what we were just talking about. So we'll start r at 0, go to r is equal to 1. And let's set up an integral now, right? So the volume, again, this is going to be a much nicer integral. It's going to end with an r dr d theta. So theta on the outside here, theta goes from 0 to 2 pi. And then r goes, so dr is the one on the inside, goes from 0 to 1. And then all we need to do is take this information right here, 1 minus quantity x squared plus y squared, and we should write in place of this, there should technically be parentheses there, we should write in place of this 1 minus, there's a slow way and a faster way. I'll just mention the slow thing because this would work in general, is just replace x with r cosine theta. There's still a square there. Replace the y with r sine theta. There's still a square there. Now this method I'm trying right now is a little slower, but it's going to work in general because whatever thing you have here just has x's and y's. So you just literally replace every x with an r cosine theta and replace every y with an r sine theta. I'll point out a shortcut for this specific. Oh, one more set of parentheses here. I'll point out a shortcut for this specific problem in just a moment. Anyway, this will be r squared cosine theta plus r squared sine theta. I don't know how many parentheses I'm going to need to draw here. Let's just go with that. I hope that looks correct. D theta equals integral 0 to 2 pi, integral 0 to 1, 1 minus, and let's see here. If you factor out an r squared, you're going to have cosine squared theta plus sine squared theta in parentheses, close parentheses, r dr d theta. Okay, finally, this part, cosine squared theta plus sine squared theta is equal to 1, right? So in the end, we would just be left with, we don't have to write that part. We don't have to write times 1. It's r squared times 1. We don't have to write that. Now, okay, so look, this works, and this is, applying this general step going from here to here, but we could actually get really, sorry, that's not even identifying the right place. It's going from here to here. Every x got replaced with r cosine theta, and every r got replaced with r sine theta. I'll just comment that we could have been, just because of the format of this particular problem, we could have been lucky much earlier if we had just noticed that right there, this x squared plus y squared, which is in parentheses, could have just directly been replaced with r squared. Okay, so we could have skipped directly down here. I just wanted to show what would happen in general, though. But now take a look at this integral. I mean, take a look at how nice this integral is. See, this earlier integral up here, this would have been really painful to do. So painful that I just kind of refused to do it. But look at how nice this integral is. 0 to 2 pi, 0 to 1. So, yeah, good thing there was a little bit of emphasis on the parentheses here, but we can distribute that. Yeah, r minus r cubed. Technically parentheses there, but I'm not really all that stressed at this point about it. Integral 0 to 2 pi. Let's see. So integrate r minus r cubed with respect to r as the variable. Okay, so r squared over 2 minus r to the 4th over 4 at 1 and at 0 d theta. So integral 0 to 2 pi. If we plug in r equals 1, we're going to get 1/2 minus 1/4. So that'll be 1/4. If we plug in r as 0, we're just going to get 0 minus 0. So I won't write the minus 0, and then there's still a d theta. Okay, and then we should now integrate the constant 1/4 with respect to the variable theta. So that'll be 1/4 theta. And we should evaluate theta at 2 pi and at 0. And so we'll get 1/4 times 2 pi minus 1/4 times 0. So let's see, 2's cancel on top and bottom. We're going to be left with pi over 2. Cool. So we're done. We've actually found a volume. And once we had avoided the standard coordinate system, the rectangular coordinate system, and we instead decided to do this in a polar coordinate system, you see, basically from here on down, that the work was actually very pleasant to do.